Thank you very much. Thank you for the invitation to speak here, and thank you for the organisers for hosting this. So my talk's on Frieze patterns and Fourier complexes, and it's joint work with these three people. So Margaret Stanier, who's with us here, Matti Vansen, who's not with us, and Andrzej Zabolotsky, who's up there. Margaret was an ex-PhD student of mine, and Andrzej is a current PhD student. Some of the figures from the talk are hosted on this website that Andrzej created, SL2 Tilings, and it's also, that website is itself hosted on Antoine's Visual Cluster Algebras site, where there are lots of other resources all gathered together, and I commend it to you. So this central figure here is the Fourier tessellation, and that is the star of my talks. It's the point of focus. So here's a short course plan. There are 3 talks on these topics. So the first talk is on integer Frieze patterns and SL2 tilings. The second talk is on Frieze patterns over the ring of integers modulo n and other rings. And the third talk is on n tilings and hypertilings. And this is new stuff it's been occupying my thoughts for the last few months, to the extent that I filled a whole notebook with my thoughts on it. But when I say notebook, I'm not talking a Ramanujan type notebook with hidden gems. It's all wrong, except for the last page where I managed to work things out with the help from my collaborators. So throughout the short course, there will be 7 exercises in algebra. There's lots of lovely algebra in this, and 3 open questions. Okay, and these 3 talks are more or less based on these 3 papers. One that was published in 2023, this one more recently with Matti and Andrzej, this middle one. And then there's a third one that's in preparation, perhaps it will be released in summer, which is with Oleg Karpenkov and then the other 3 that I've mentioned before. So, before I get going properly, I'm going to take a tour of some of the Frieze patterns that we will meet. And these are all Frieze patterns, they're all of this sort of type. They're all Coxeter type, Conway-Coxeter type Frieze patterns. So here's one of the sort that was shown in Christina's talk, where there's zeros at top and bottom, positive integers in between, and it satisfies the diamond rule. If you take any diamond of 4 integers and multiply these two, 3 5 is 15, minus 7 2 is 40, then we get 1. So that's the diamond rule that's satisfied throughout the Frieze pattern. So we'll start with those. We will also look at Frieze patterns over the integers. So you can see that this one now has integer entries, some of them negative, some of them are 0. And the second last row, this time, comprises minus 1s. Okay? And I allow that kind of flexibility. So we can have minus 1s. We will look at infinite Frieze patterns. So these are like the normal sort, except there's no bottom to them. They go down and down and down forever. And this is one of the most attractive Frieze patterns of this type. So it's just like the sort of standard Conway-Coxeter Frieze pattern, but go down, 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 down. We will look at this Frieze pattern, which I've called Zabolotsky's non-periodic Frieze pattern. I think we should be naming our Frieze patterns more. So I've named this one after my PhD student, Andrzej, who pointed it out to me, and it surprised me because I hadn't realized that it would exist. So what is it? What's special about it? Well, the entries are rational numbers, and the second last row this time, you can see comprises 2, half, 2, half, like that. So I'm allowing that kind of flexibility with rational numbers. The key thing about this one is it's not periodic. If you look at the middle row, then the even terms are halving each time, and the odd terms are doubling each time. So it's clearly not periodic. So it's a curious sort of object that I didn't realize that it exists when I first started out on this. We will look at Frieze patterns over other rings besides the integers. So this one's over the ring of integers modulo 6. It looks like the infinite Frieze pattern, but take a look at the second last row. That's just consists of 5s. Why are we allowed that? Well, because 5 5s are 25, which is congruent to 1 modulo 6. So we could then close that up with zeros. The diamond rule is satisfied for this Friese pattern when we're in the ring of integers modulo 6. So in the second talk, we'll look at modeling these objects. This one is a Friese pattern with 2s in it, you see? So it doesn't really satisfy the diamond rule. It satisfies the diamond rule, but with 4 instead of 2. AD minus BC is equal to 4. Now, you can always get Friese patterns with 2s from Friese patterns with 1s by multiplying all the entries of a Friese pattern with 1 by 2. That's one way of obtaining a Friese pattern with 2s. This one here is not of that type, though, because it's got odd numbers in it. So it doesn't come from a normal Friese pattern. It's something different, and I was interested in investigating where these come from. So just imagine dividing every entry of this Friese pattern by 2, and what we get is this. So this is a positive rational Friese pattern, and I'm going to discuss these in my third talk. Really, it's not any old, the entries aren't any old rational numbers. They all lie in half z. And more generally, I'll look at Friese patterns with entries in 1 over nz for some positive integer n. So that's a tour of the Friese patterns that we'll look at. Now I'll move on to part 1 of my talk, which is integer Friese patterns and SL2 tilings. I'm going to take motivation for this from Dessin d'Enfant. And the reason for this is because in the theory of Frieses, triangulations abound. And the theory of Dessin d'Enfant is all about triangulations. So we're going to start, that's going to be our route into the subject. And at least that was my route into the subject. So it has sort of historical significance for me. And to look at Dessin d'Enfant, I'm going to begin with this famous quote of Grothendieck from 1984 in this proposal that he wrote. And I'll read out the English version. It says, there is a profound identity between the combinatorics of finite maps on the one hand, and here he means cartographic maps, not maps from A to B, and the geometry of algebraic curves defined over number fields on the other. This deep result, together with the algebraic geometric interpretation of maps, opens the door onto a new unexplored world, within reach of all who pass without seeing it. So let's take a little look at what this means. So we begin with a compact surface. Okay, for some of what I'm about to say, the surface doesn't need to be compact, but let's just go with compact, because some details will require that. And we're going to take a map on the surface. What is a map? Well, a cartographic map, it's a graph embedded on the surface such that each component of the complement of that graph is a simply connected region. So it's like taking a compact surface and splitting it up into polygons. There's a bit more to it than that, because you could have multi-edges and you can have vertices of degree 1, but forget that stuff. Just think of polygonal decomposition of a surface. And there's 50,000 papers written on this by people generalizing platonic solids to other surfaces and that type of thing. So that's our map. Now what we're going to do is we're going to introduce a white vertex on every edge, like this. So now our graph has become a bipartite graph. It's a bipartite graph in which every vertex, white vertex, has degree 2. We could also think about bipartite graphs where some of the vertices are not degree 2, like that there. I snuck in an extra pair of edges. And this is more or less what a dessin is. It's an embedding of a bipartite graph on a surface, a compact surface, where all of the complementary components are simply connected. I'm going to take an extra step, which is I'm going to introduce another vertex, another set of vertices, red vertices this time, one in the center of each face. And then once I put those red vertices in, I'm going to connect them to all the white and black vertices, like that. Okay, one more step. I'm going to shade in the triangles, some grey or black and some white. And so there are two types. There are the red, black, white ones and the red, white, black ones. So they come in two flavors. In this way, we get a tessellation of the whole surface by black and white triangles. Next, I'm going to construct a ramified covering map as follows. So this is a picture. It looks like a disk, but it's meant to be a sphere. In fact, it's meant to be a sphere comprising two triangles, a black one and a white one, with red, black, and white vertices. You might not be able to see, but this is red, that's black, that's white. So I've taken a black triangle and white triangle and sewn them together like a pillowcase. Now you can imagine constructing a ramified covering map from X, from this surface up here, to the sphere by mapping black triangles to the single black triangle, white triangles to the single white triangle. All the red vertices go to the single red vertex down here. All the white vertices upstairs go to the single white vertex downstairs. And we do this in a compatible kind of way, such that the map is an orientation-preserving homeomorphism from each black triangle upstairs to the single black triangle downstairs, and so forth. I hope you get the idea. So this is a ramified covering map. It's ramified at the three distinguished vertices down here. These are the ramification values, red, white, and black. In this way, we can take the complex structure on the Riemann sphere and lift it up to a complex structure on the surface, making X into a Riemann surface. There's a bit of an issue with the vertices, but that's not really a problem. You can sort that out. So what's happened? We started with just this combinatorial object on a surface, and by this process, we've made it into a Riemann surface. So there's a Riemann surface structure naturally associated to the map, to the descent. But there's much more than that, because every compact Riemann surface can be described by an algebraic curve, either affine or projective. So some sort of equation like w squared equals az to the 7th. This is just an example. Something like that. So this complex curve would describe the Riemann surface. And Grothendieck was aware of Belyi's theorem. So Belyi's theorem says that a compact Riemann surface X can be defined over the field of algebraic numbers Q bar. That means that these two are in Q bar, they're algebraic numbers, if and only if there exists a non-constant holomorphic covering map from X to C hat, the Riemann sphere, ramified over at most 3 points. In the circumstances we have here, we do have a holomorphic covering map ramified over at most 3 points. We constructed one. So this Riemann surface is, this compact Riemann surface is of the type described in Belyi's theorem. So it must be, as an algebraic curve, it must be defined over the algebraic numbers. So it looks something like this. And why is that of interest to people in dessin d'enfant? Well, a lot of them are interested in the absolute Galois group, the field automorphisms of the set of algebraic numbers. And these act on algebraic curves. And by this process, they act on dessin. So you can get some understanding of this notoriously complex group by looking at the action on dessin. OK. But the story continues. Oh, yeah, but first, here's a famous picture of a dessin that will come up several times in my talk. It's from Felix Klein. It's a picture of the Klein quartic. So this is one of the earliest pictures of dessins, I suppose. And it looks very complicated, but there's some identification of the sides such that when you glue things together, you get a genus 3 surface, the Klein quartic, which is described as a projective curve by this equation here. And there are 168 black triangles and 168 white triangles corresponding to the automorphisms of this surface and the automorphism groups PSL27. So I said the star of these talks was the fiery tessellation, but actually there are two stars. The other star is this group, SL2Z, the group of 2x2 integer matrices. There's an important subgroup of SL2Z, which I'll introduce now and talk about more in due course. So this will be a bit sketchy now, but there'll be more later. So this is the principal congruent subgroup of level 2, which is this group here, where A and D are odd and B and C are even. Now the group SL2Z has torsion. It has elements in it of finite order. Gamma 2 doesn't have elements of finite order, apart from plus or minus, apart from the identity and minus the identity. But forget about those. More or less doesn't have elements of finite, non-trivial elements of finite order. In fact, gamma 2, if we quotient out by plus minus I, don't worry too much about that detail. It's an abstract group. It's the free product of two infinite cyclic groups, and it has the important property that when we look at the action of gamma 2 on the unit disk, don't worry too much about this now if it's not familiar to you, because I'm going to come on to this sort of thing later. Then when we take the quotient of the unit disk by gamma 2, then we get the thrice punctured sphere. We can now use arguments, standard arguments from covering space theory that I've illustrated here. So we take the thrice punctured sphere. This is like the pillowcase we had on the previous slide, but now the three vertices, I'm making them punctures. Its universal covering space is the unit disk. So there must be some subgroup G of gamma 2 such that X star, where X is our Riemann surface where I put punctures at all the vertices, is equal to the quotient of the unit disk by some subgroup G of gamma 2. This has two important consequences. The first is that the Riemann surface structure on X, or X star, we can recover that by taking the quotient of D by G. So that's another route into getting its Riemann surface structure. That's one. The next important thing is that this endows X star with a hyperbolic structure, because D comes with a hyperbolic structure that I'll talk about in due course. And we can take the quotient of that by G, and this gives us a hyperbolic structure on X star. There's one more important consequence, which I've illustrated on my next slide, which is if we think about the unit disk in my top picture there, not just as the unit disk, but also with this fiery tessellation imposed on it. So this tessellation by triangles. I'm going to talk a lot more about this in subsequent slides. Well, what gamma 2 does, roughly speaking, is it takes a black and a white triangle and stitches them together, like I mentioned earlier, like a pillowcase, to give us this object down here. So that's what gamma 2 does. When we look at the action of G on the unit disk with the fiery tessellation imposed on it, and we take the quotient of that by G, we get our triangulation on X that we had earlier. And every triangulation arises in this way. Yes?
So let's understand on which structures the Galois group of Q-bar is acting. So I'm wondering, so if you start with an algebraic curve defined over Q-bar, you said they exist by the very theorem cover of the three-puncture sphere.
Yeah.
How unique is that? How unique do you have this? Is this a correspondence between, is it a bijective correspondence between maps de Saint-Enfant and curves over Q-bar? Or are there several maps, possible maps?
There are several.
There are several. So
Yeah.
you do not get an action of Galois Q-bar over Q on the set of maps?
Up to certain equivalences, we do.
Up to certain equivalence?
Yeah.
And so up to the action of the mapping class group, maybe? Or something like that?
quite possibly that's beyond what I can tell you.
Then maybe another question would be, so we also can get an action of Galois group onto subgroups of C2Z because these are giving you these covers, but again, up to something. Is that, in that situation, do you know what the something is? To conjugate C,
No, I'm not totally sure. I'll talk more, but I'll have a think and talk about it afterwards. Okay, and I learned about this this procedure from David Singerman and in this paper from 1988. So what this shows us is that when we're considering triangulations on surfaces, the Fari tessellation is a universal triangulation and is clearly of great importance. Okay, so let's take a closer look at this object, the Fari graph, as I called it. So we're kind of going to take a few steps backwards now and introduce some of the things that I just brushed over before. So the hyperbolic plane is the upper half plane, H here, endowed with this Riemannian metric. And I will switch freely between this model of the hyperbolic plane and another model of the hyperbolic plane, the unit disk, by some conformal map going between the two. I've drawn the two types of hyperbolic lines in the upper half plane here, a semicircle orthogonal to the real line and a vertical line. In this model, the hyperbolic lines look like Euclidean diameters or arcs of circles that are perpendicular to the unit circle. Now the group SL2R acts on H as a group of isometries. So how does that work? We have SL2R and we have the hyperbolic plane and we have a matrix A, B, C, D in SL2R. It takes a complex number Z and it acts on it by Mobius transformations, giving us AZ plus B over CZ plus D. The ideal boundary of H is R union infinity. It's not part of the hyperbolic plane. So this is sometimes called the boundary at infinity. And so this is the ideal boundary for the hyperbolic plane, and the unit circle is the ideal boundary in that model. So I won't say too much more about plane hyperbolic geometry, but I'll include this picture of a model created by Beltrami, and it's an illustration of what the hyperbolic plane would look like if you try to embed it within R3. Now, it's not possible to do this in a smooth way. So what this represents is a small piece of the hyperbolic plane embedded in R3. And what do the crinkles represent? Well, what you should think about them is that in hyperbolic space, there's lots of room. So as you move away from the origin, there's lots of space. So if you try to embed that sort of geometric object in R3, you need lots of folds in order to represent the forever expanding circumference of a growing circle. So that's quite a nice way of getting a bit of a feel for the hyperbolic plane. Right, onwards. Now, triangles in the hyperbolic plane they tend to look like, they're thin triangles. They have this sort of structure where these angles together sum to less than pi. Now, among all triangles in the hyperbolic plane, there's one of a very special type called an ideal triangle. This one has 3 vertices on the boundary, and it's essentially unique. It's unique up to congruence. So there are 3 vertices on the boundary, and the 3 angles must be 0. So in a sense, it's a triangle that's as big as possible. It's got area pi. Now I'm going to do a special trick. What I'm going to do is I'm going to take one of the sides of this triangle, any one of them, and perform a hyperbolic reflection in that side. And when I do that, we get this kind of object. So I've reflected in one side and got another triangle. Now I'm going to do the same process again and again. reflecting and reflecting, and we get this sort of object appearing eventually. This is by many reflections. And this is the Fari tessellation. So it's a tessellation of the hyperbolic plane by ideal triangles, but not any old tessellation. It's a special tessellation generated by this highly symmetric process. So we should expect the resulting object to be rich in symmetries, as indeed it is. Okay, the next slide, I'm going to do the same thing, but this time in the upper half plane. You know, I said I'd switch freely between the disk and the upper half plane. So we're going to do that, and we're going to take a distinguished triangle, one with vertices at 0, 1, and infinity. And if we do the process with that not only will we retain the rich geometric structure, but we will also get a rich numeric structure to complement the geometric structure because of our careful choice of vertices. So we reflect in any which way. It doesn't matter what you do, which way you do it in. Reflect, reflect, reflect. And then we end up with this sort of picture. And this is what people usually think of as the Fari graph. There's a concise way of describing the Fari graph. You don't have to do lots of reflections. You could dive straight in with this definition. So the Fari graph is the graph with vertices, the rational numbers, and infinity, and with edges comprising pairs of vertices, A over B and C over D, that satisfy AD minus BC equals plus minus 1. So if we do the process that I described in the previous slides, we end up with this. Trust me, we do. Yes, and the edges are represented by hyperbolic lines, or at least I've chosen to represent them by hyperbolic lines here. Okay, so that's an important definition to remember for these talks. So just to talk around it a bit more, there are some familiar concepts that you will probably have seen before. So if we take two adjacent vertices in the Fari graph, A over B and C over D, and form their Fari sum, which is where we add the numerators and add the denominators. This is what is called Fari addition. It's a handy arithmetic operation which we can use to generate the Fari graph in yet another way. So let's do it. We're going to start with this part of the Fari graph with 0 over 1 and 1 over 1. Perform Fari addition, add the numerators, add the denominators, we get a half. Let's do Fari addition again on these two pairs. 0, 1, 1 over 2. Adding those will give us a third. Adding these will give us 2/3. And if we continue ad infinitum, then we recover the Fari graph. So this is a sort of computational way of obtaining the Fari graph or Fari tessellation. And here I've put a cutting from this paper written by John Fari on a curious property of the vulgar fractions. So John Fari was a geologist, and he submitted this short note to the Philosophical Magazine in 1816, where he made some observation about Fari sequences, or Fari series as they're normally known. And he phrased it as a question. The question, and I think it had been noticed by other people before, so he wasn't necessarily the first, but so, you know, that's how it is in maths. Anyway, the question was picked up by Cauchy, who solved it, and what with Fari having a distinctive surname, he got attached to the concept. And so it's remarkable that just submitting this short note, he led to such profound thoughts in mathematics following this. And it's of particular interest to me because John Fari Sr., I put John Fari Sr. because his father was also called John Fari and his son was called John Fari as well, which is quite ridiculous. But anyway, John Fari Sr., he worked in Woburn for the Duke of Bedford, which is where I happen to live. Yeah. And I contacted the Duke of Bedford estate to ask them about John Fari. What do you know about him? And they didn't know anything whatsoever. There we have it. Okay, automorphisms of the Fari graph. You can see that the Fari graph has some obvious symmetries. For example, if we put in these red spots here, then about any of them, there is a rotation of order 3 symmetry. Okay, it's a hyperbolic rotation, so it looks a bit distorted for our Euclidean eyes, but there are hyperbolic rotations of order 3 about any of these red vertices. There are also rotational symmetries of order 2 about the green vertices. So 3 and 2. And in fact, it's not very hard to show that the full automorphism group of this tessellation is, as an abstract, it is formed by compositions of the red and green rotations. Now, if we illustrate, now I've moved to the upper half plane model, as I promised to do. If we illustrate those two rotations by Mobius transformations, just ignore the blue one, the red one and the green one. This is the red one, rotation of order 3. Here's the green one, rotation of order 2. So these two matrices here, this is the green one, this corresponds to the red one, and these two you can easily check. They generate the group SL2Z. So what I've shown, not in detail, but shown roughly, is that SL2Z is the group of orientation-preserving automorphisms of the Fari graph. And it acts transitively on directed edges. Okay. I'm going to mention a couple of other models of the Fari graph that will come in useful for later talks. One is using Ford circles. So a Ford circle, this is where you take, this is the upper half plane, and we draw at the rational A over B, we draw a circle of diameter 1 over b squared, centered at A over B. And these are called horocycles in hyperbolic geometry. So for every rational AB, we do this. And we end up with this kind of picture. You can see it superimposed with the Fari graph. In the next slide, I've got rid of the Fari graph and just left the Ford circles. And this is a lovely model of the Fari graph. The vertices are now replaced by horocycles, and edges are represented by tangent horocycles. So I'll make use of this later, and I'll just highlight why they're called Ford circles. They were introduced by Lester Ford in this paper in American Math Monthly, which I recommend. And I won't talk about it much, but it has a way of describing continued fractions. And he talks about these Ford circles as being like clocks. And he has this sort of pattern going on where these are clocks. And the numbers here are coefficients of continued fractions. It's good fun and worth a read. In the background to my talk are continued fractions, which I'll speak of briefly. So the continued fractions that I work with are 1 minus continued fractions. So normal continued fractions have pluses here, but the ones that lend themselves better to this theory are minus continued fractions. I can't do it, there it is, with minuses here instead. There's not a lot of difference between working with plus and minus ones. You can make this sort of, I've indicated the kind of transformation between the two down here. Now the thing about minus continued fractions is that they correspond to paths in the Fari graph. So I'm going to illustrate this rather than proving anything. So here I have just some random continued fraction expansion of 3/4. And yeah, I've got negative integers. Some of the coefficients are negative integers, but that doesn't matter. Here, I'm at the bottom here, I put the first convergent. The first convergent of this continued fraction is 0. and I've also drawn a line from infinity to 0. The next convergent is 1, and I've drawn another line, and then we get subsequent lines like this. So the point here is that the convergence of this continued fraction they give rise to a path from infinity to that number 3/4. Okay? So think continued fractions, paths. That's what I'm trying to show. And I've got a few more examples just to show what I'm talking about. Here's a path, another path from infinity to 3/4, and there corresponds a different continued fraction. Here's another path, and here's a really short path. So each path gives a continued fraction. Overall, what I'm trying to tell you is this. Yeah, it's a theorem that I stated roughly. For any integer, there's a one-to-one correspondence between integer continued fractions and paths from paths of length n beginning at infinity. So there's going to be lots of paths in these talks. One last model of the Fourier graph. In fact, this is the jewel of the Fourier graph. So up here, we've got the Fourier graph, or the Fourier tessellation, and I've drawn its dual graph here. And down here is another copy of the dual graph, but with the Fourier graph now removed. And you can see that it's an infinite trivalent tree. So it's a tree where every vertex has degree 3. And this was used by Conway to classify quadratic forms, and there's a lovely exposition of it in Hatch's book, The Topology of Numbers. If I get time tomorrow, I'm going to talk about something involving quadratic forms where we'll use this topograph. Okay, finally, I finished with the Fourier tessellation, and I'll now move on to discussing Friese patterns, covering some ground that Christina covered earlier. So here's a Coxeter Friese pattern, and it satisfies the diamond rule. We've seen these a few times already. And an infinite strip of integers of this type is called the positive integer Friese pattern. That's what I'll be calling it. And every positive integer Friese pattern is periodic. In fact, they have a glide reflection symmetry. So periodic means kind of like there's chunks like this that are the same, but in fact, there's something a bit stronger, that there's a glide reflection symmetry. So they're kind of triangles that you flip and flip and flip like this. So they have that sort of symmetry. And there's an observation that each positive integer Friese pattern is determined by its quiddity cycle, the periodic part of its third row. This is exactly what Christina showed us earlier, that if you put in the third row, then using the diamond rule, you get the fourth row, then you can get the fifth row, and so forth. So this finite string of positive integers determines the whole Friese pattern. Now, triangulated polygons we met earlier. So they're polygons partitioned into triangles by diagonals. And here I'm copying Christina, and I've put the number of these numbers indicate the number of triangles incident to each vertex. So this is a 4 because there's 1, 2, 3, 4 triangles incident to it. And Conway's insight in this elegant paper by Conway and Coxeter was that there's a correspondence between triangulated polygons, these, and Friese patterns. So here's one, if you read these numbers around the outside, 1, 2, 2, 3, 1, 2, 4, then you can see 1, 2, 2, 3, 1, 2, 4, 1, 2, 2, 3, 1, 2, 4. So there's the correspondence, which we've met already. And here I put there is a one-to-one correspondence between, this is just the sort of rough statement of the theorem. Now, I find the Friese patterns community agreeable, but there's one thing we can't agree on, which is the definition of width. Yeah? For me, width is the number of rows minus 1. And the reason I've chosen that is because then we get width n and triangulated n-gons here. Other definitions of width exist. I should actually say that we do agree up to an additive constant on the definition of width. Okay, right, so for these freeze patterns, all the entries were positive. If we remove that restriction and allow negatives and zeros, then we're in wild territory. For example, in this freeze pattern here, oops, that I've jumped past, the asterisks, they can be any entries at all. So evidently, this freeze pattern can be non-periodic. The asterisks, if you sort of work out the diamond rule, they could be anything because there's loads of zeros that sort of get rid of them. Okay, I haven't got that much to say about wild freeze patterns, but just beware of them. We will look at freeze patterns with negative and zero entries, but they will all be tame. Yeah, we met tame earlier, and I'll talk about it a bit more in due course. Okay, now when people first start studying freeze patterns, they're liable to make some basic errors. So I'm warning you about them now, right? The first of these errors is called the tapering freeze pattern. This is where you start with some zeros, start with ones, and then you construct the diamond rule to construct the next row, and then the next row, and then the next row like this. And then you find that you've only got a small bit of a freeze pattern. You've missed all the stuff here and here. Okay? And the reason is when actually you do this from row to the next when constructing a freeze pattern, you've kind of got to pretend that there's an entry here, and then if that entry was there, then I'd have to put something or other there. And if you remember to do that, then you get the full freeze pattern. In fact, in this case, it's worked out okay because I happen to choose a periodic part. I choose the whole quiddity cycle here. So in fact, this triangle sort of nicely indicates the glide symmetry, a fundamental region for the glide symmetry of a freeze pattern. So that's the first mistake that you should watch out for if you're new to freeze patterns.
What's the mistake?
Don't make me labor the point. The mistake is that if you wanted to draw a decent sized portion of the freeze pattern, then you have to if you want to get this part of the freeze pattern, then you have to pretend that there are entries here to help use the diamond rule to help you construct these. I refuse to say any more about it. It's really not important. Yeah. I'll talk to you afterwards. Yeah. So the next mistake is I've called it the fraction. So this is where you calculate one row after the next, and then you get a fraction turning up. And you think, oh, that's unusual. I don't normally get fractions when I do this. And then you continue like this. Now, I warn you that the fraction is usually followed by the massive fraction. And when that happens, you know to abandon ship. In fact, if you get a fraction, then what has happened is that there's been a mistake. Because, for my first exercise, the exercise is to prove that if the quiddity sequence, the third row, of a freeze pattern comprises integers, then all entries of the freeze pattern are integers. Yeah, there's some tameness issue here as well that I'll come to in a minute. So you shouldn't be getting fractions. If you do, you've made a mistake. And here I'm really thinking about any old freeze patterns, not necessarily Conway-Cox to ones where you could go on forever downwards. But the third error is I've called zero. So this is the same freeze as last time, except now I've changed this fourth row. And you carry on like this. This is all fine. But now you come to an issue here, because we've got two minus ones here. Their product is 1. So what is this entry going to be? Well, it could be anything, right? For the diamond rule. So we might as well let it be 1. Okay? Because it gets multiplied by 0, so 1 would be okay. Don't do that. Don't let it be anything. In fact, what you have to do is, as Christina indicated earlier, you draw a diamond around that 0, and then what you need is for the 4 corners of that diamond to sum to 0. Yeah, so here we have 1, 1, 2, and minus 3. They sum to 1, so this is wrong. You shouldn't choose minus 1, choose 1 here. It should, in fact, have been another 0. And this is tameness. This is essentially tameness. So if you want your frieze to behave well and you want to respect tameness, then make that a 0.
Just to clarify, the sum rule is determined in 0 in this class.
Yeah. SL2 tilings. So what we're going to do now is going to take our frieze pattern and rotate it by 45 degrees to get, once we've rotated it by 45 degrees, what happens is that this diamond becomes a square. It becomes an element of SL2Z. So we rotate, and then we take lots of copies of the frieze, and we cover the plane in them like this. A positive one and a negative one, positive one and negative one. And we choose positive then negative in strips like this, so that this has determinant 1. If we'd made this another positive strip, we'd have determinant -1 there. Object that we obtain of this form is called an SL2 tiling. More generally, here's SL2Z again, and we define an SL2 tiling to be an infinite array of integers such that any 2 by 2 submatrix satisfies AD minus BC equals 1. And when I say submatrix, I really mean submatrix stuck together. You can't have 4 entries out here or anything like that. So that's an SL2 tiling. And this one, I first learned about SL2 tiling from Peter Jorgensen, and he showed me this one. I think he credited it to someone else, actually. But this is where you just take the numbers 1, 2, 3, 4, 1, 2, 3, 4 on the axes, and then fill out all the gaps. And that's a rather lovely SL2 tiling. And SL2 tiling is tame if the determinant of each 3 by 3 submatrix is 0. So this is the tameness property that I introduced just before. Exercise 2 is about the tameness condition. I think I only really understood tameness well when I encountered this formula for determinants, which is called a special case of Dodgson condensation. So these vertical lines are meant to indicate determinants here. And roughly speaking, it says if we have a 3 by 3 matrix like that, and let's call it X, and then you split it into 2 by 2 submatrices like this. So call this one A, B, C, D, and let's call the little middle entry E. Then we get E times the determinant of X is equal to the determinant of A times the determinant of D minus the determinant of B times the determinant of C. If this 3 by 3 submatrix lies within an SL2 tiling, then these guys are all 1. These are all 1, so this is equal to 0. So you can see that E times det X is 0. So if all the E's are non-zero, if we have a positive integer SL2 tiling, then we have det X is equal to 0. So we get tameness. So this is why the consequence is immediate. Positive integer SL2 tilings are tame. The only time when we sort of could possibly have a 3 by 3 determinant non-zero is when we have a 0 entry. And that's why you get these wild SL2 tilings. And there might be some sort of wildness around the 0. Right, but I'll say no more about those now. Frieze patterns from the Fourier graph. So an observation is that if you take any triangulated polygon, you can embed it into the Fourier graph, like so, for example. So here's a pentagon, a triangulated pentagon embedded within the Fourier graph. This observation was made by Sophie and Valentin and Sergei Tabachnikov in this charming paper from 2015. So they reprove Conway and Coxeter's results using the Fourier graph. And I've illustrated it here. So we take a triangulated polygon, embed it in the Fourier graph, like this. There's lots of ways of doing it, all essentially equivalent. And here's the same picture, but in the upper half plane model. From this picture, we get a path around the outside, and this path they use to establish Conway and Croxter's result. So this was kind of my starting point into this subject. Now I'll talk about SL2 tilings from the fiery graph. So here we have an SL2 tiling, right? And I've shaded in 2 consecutive rows and 2 consecutive columns, red and blue. Now what I'd like to do is, for the rows, say, let's call the tops, let's call them AI, and let's call the bottom row BI. And we're going to form fractions like that. If we do that all the way along, then we get a path, gamma. This path has the property that AI minus 1, BI minus 1, AI is equal to 1. This just comes from the SL2 tilings property. So you can see that gamma is a path in the fiery graph. A bi-infinite path. We can do the same thing with the columns instead. Cj for the left-hand row over dj for the right-hand row, divide one by the other, and we get another path delta. So an SL2 tiling gives rise to 2 paths. We could choose different rows and columns, but that would give similar sorts of paths.
Wait, where were the A's and B's coming from again in this picture?
The A's are these, and the B's are these. I've just divided the top row by the bottom row, in a sense. And over here, the C's are this column, and the D's are this column. That's it. So then I had this theorem here that says that there's a one-to-one correspondence between pairs of bi-infinite paths and tame SL2 tilings. So what we can see here, so roughly it says pairs of paths and tame SL2 tilings. What I've shown you here is if we start from an SL2 tiling, I've shown you how to obtain 2 paths, gamma and delta. So I've sort of done that way round from the correspondence. The other way round works like this, that if we start with 2 paths, AI over BI and CJ over DJ, then we can form an SL2 tiling using this formula that I've written on the board. AI DJ minus BI CJ. And I'm going to talk a bit more about this in my next talk, why this correspondence works.
So the 2 paths, you don't need to say where they intersect.
No, they might not intersect.
No, what I mean is in the columns, like in the SL2 columns, you choose two lines and 2 columns, and so you've got this intersection, which is a 2x2 matrix.
Yeah.
And so in the 2 paths, you choose your paths to be, I mean, you could move one path and leaving the other one fixed.
Yeah.
It's kind of changing one and changing the matrix. So what do you mean by saying, my question is 2 paths up to what? It's just the pair of paths simultaneously in the picture is going to give you a single SL2 tiling, and that's going to fix the intersection.
First thing to say is that there's a sleight of hand that I missed out. I described how to get 2 paths, but in fact, for all this to work out, you have to transform one of the paths by an element of SL2Z to get all the algebra to work out correctly. But this way round, if you take any two paths and apply this formula, this gives you an SL2 tiling. If you take, so if A is in SL2Z, and you take this pair of paths, this will give the same SL2 tiling. If you do that, that will give you something different. So you have to take some care about these things. Okay, so I'll do a few quick consequences of this and then wrap up. So one of my favorite parts of this is that is how this gives us insight into positive integer SL2 tilings. Well, let me describe this very briefly. So we have two paths, AI, BI, and CJ, DJ. And we can normalize so that the BIs and DJs are positive. After all, if we multiply this by top and bottom by -1, then we get the same fraction. If observe that AI minus 1 over BI minus 1, a quick bit of algebra, minus AI over BI is equal to, it's 1 over BI minus 1 BI times AI minus 1 BI take BI minus 1 AI. That is just 1, so this is greater than 0. So that's observation 1. Observation 2 is that AI over BI minus CJ over DJ is equal to, well, similar sort of algebra, 1 over BI DJ, AI DJ minus BI CJ. So if these two paths come from a positive integer SL2 tiling, which is what I'm talking about at the moment, then this is positive, because this is just Mij, according to my formula up there. So this is greater than 0 as well. So we see that that is greater than that, and that is greater than that. So if we now try to draw these, I'll just do it at the bottom here, on the phyrograph. Well, the first path is decreasing, like this. And the second path, that's also decreasing. And the first path is bigger than the second path. This is very roughly what this algebra tells us. So we have two paths that look like this, which is the sort of pictures that I've got up there. You see two paths, both running clockwise, and neither of them intersecting the other. As soon as you intersect, you get a 0. Yeah, and so what's important about these, what's worth studying is they have 4 distinguished endpoints. Yeah, the limits of these two monotonic sequences. And you can see in this example here, so here's the SL2 tiling I mentioned earlier with the 1, 2, 3, 4 SL2 tiling. And its paths here are very particular types. Because the blue path, the backwards limit point of the blue path is equal to the forwards limit point of the red path. And the forwards limit point of the blue path is the backwards limit of the red path, -1 and 1. So this is really very unusual circumstance for these paths. Gives you an SL2 tiling with particularly small entries.
If you fix the 4 endpoints, they are kind of the biggest paths, the largest paths. But for instance, in your red path here, between infinity and 2, we could have subdivided it by going through 3, right? That would still be a valid path.
Yep.
We could have done infinity 3, 3, 2.
Yep.
And so there's a non-unicity, actually. Like if you know the
Hang on, 100. We could have done infinity 3, then what?
And then 3, 2.
No, we'd have to go through 2 first. Yeah, 2 sort of separates them. Yeah, it looks like this. Here's
Oh, right.
2.
Oh, so you're saying that the endpoints you need to determine oh yes.
Yeah.
The endpoints determine the path.
No.
The two endpoints determine the path.
No, no, no. No, very far from it. No.
You map it one way. You have the SL2 tiling, you get the 4 points, but you haven't said anything about going back.
Yeah.
But there's a preferred path with these two endpoints.
There is a sort of maximal type path. Yeah. Good point. Okay, and then there's a bit more to say on this, but I think that given that I've got 3 talks, I oughtn't to overrun on this first one. So thank you very much. That's it.
Okay, thank you very much. More questions?
I can project.
Okay, yes, you're.
Under your correspondence, you have these pairs of bi-infinite paths going to SL2 tiling. And you can act on each SL2 path, each path of this varied triangulation by an SL2. Under your correspondence, if I understand correctly, if I act on both paths by the same element in SL2, it doesn't change what the corresponding tiling is.
That's correct.
But if I act on just one, it gives some non-trivial action on this side that presumably corresponds to a non-trivial action on the other. Do you have any sense for what that SL2Z action is on the SL2 tiling?
Well, these two paths that intersect at a matrix, and maybe the action of the SL2 is maybe kind of translating this matrix, and then so we've got 2 paths in there at the time, like 2 line and column of this SL2 matrix, and so you're acting maybe on this matrix, leaving this one fixed.
How are they intersecting? Are they?
No, in the triangle, but the line and the column.
Okay, I see
So
what
the
you're
path,
saying.
and these intersect in the matrix. And if you're acting on one column, kind of changing this one here, and maybe you can view it
So you're just saying a multiplication action on a column?
on the 2 columns.
I'm not sure I have so to complement that answer. I'm not sure I'll hit. Oh, it's the forget that one. Perhaps I'll just mention something very briefly. I think there's maybe a politician's answer where I actually answer a different question, but let me do it anyway. So this Mij is equal to, well, it's Ai dj minus Bi Cj. This is equal to Ai Bi times, we have this symplectic form. So if we want to obtain a 2x2 block from the SL2 tiling, this 2x2 block is equal to something like this. And that matrix by this. Okay, now if we were to act by A in SL2Z on this and this, it would be like putting an A transpose in there and an A in there. And what you'd find is that this whole thing would just give us this again. If we just put an A in there, then it would be like, replacing this with some other object instead. And this is the effect it would have, at least in this 2x2 case. Overall, I'm not sure I have a great understanding overall of what might happen.
Okay, maybe view of the schedule, we relegate other questions to the lunch break. And let's thank Ian again.